first analysis program, we looked at a very important property of real numbers, the completeness axiom. And in the second analysis program, we looked at functions, and we learnt how to picture them visually as graphs. Now, in this analysis program, we're going to bring these two ideas together, and we're going to look at a particular property of functions, continuity. Intuitively, a function is continuous if its graph doesn't have any breaks in it. For instance, here's the graph of a function from R2 to R, and it's nice and smooth, and it doesn't have any breaks in it. And here's the graph of a function from R to R, a fairly familiar function, and that doesn't have any gaps in it either. Now, one way of expressing mathematically that a function doesn't have any gaps in it is to say that it maps an interval in the domain to an interval in the codomain. But that won't do as our definition of continuity. Let's look at this function. It's a function from R to R, and it's given by f of x is sine 1 over x for x non-zero, and f of 0 is 0. And here's what the graph looks like. It wiggles faster and faster as you get nearer to the origin. So all you can see in here is this solid block of colour. If I take any interval in the domain, then it maps to an interval in the codomain, and it's pretty clear for intervals that don't straddle 0. But if I take an interval that straddles 0, like that, then it just maps to the interval -1 plus 1. So this function does have the property of mapping intervals to intervals. But it's not the sort of function we want to regard as continuous. And the reason for that is, if we think about measuring things in the real world, for instance, a length or a weight, all we can do when we're measuring something is to get it within a certain error bound. So all we can do is to say that it lies in a certain small interval. So the functions that are important physically are the ones that take small error intervals to small error intervals. And this function doesn't have that property because, you see, however small an interval I take about 0, the image is always this interval -1 plus 1. It's not small. So our definition of continuity is going to say that the function takes a small enough interval to a small interval. In fact, here's the precise definition. We look at an arbitrary point C in the domain of the function, and we look at nests of intervals converging to C. Each nest of intervals gives rise to a sequence of image sets, and we want these image sets to form a nest too. Well, it's a more complicated definition than mapping intervals to intervals. As a matter of fact, it's a rather better definition. Let's see how it copes with functions that have a break in them. Here's a function with a rather obvious break. It's a function which has the value 1 if x is less than or equal 1, and 2 if x is bigger than 1. So it's got a break at the point 1. And let's see what happens if we apply the definition of continuity, choosing a nest converging to 1. Well, any interval in the nest is going to be like this, with 1 in the middle, and it's going to have for image these 2 points. These points are going to go over to here, and these points are going to go over to here. Well, there's a technicality in the definition of continuity which I didn't tell you about. Before you look to see whether the images form a nest, you have to take the least closed interval containing them. So in this case, we'll get the interval 1, 2, like that. And when I consider a whole nest of points converging to 1, a whole nest of intervals converging to 1, then each one of these intervals is going to have for image, when I close it off, take the least closed interval, this same interval. So the intervals over here won't form a nest. So a function like this that does have breaks in it isn't going to be continuous according to our definition. Well, what we're going to do with our definition of continuity in this program, we're going to do two things. At the end of the program, we're going to look to see how the definition generalizes for functions from R2 to R and from R to R2. But before we do that, we're going to give a precise proof of that property, the intuitive property that a function that's continuous maps intervals to intervals. Here's Peter.
Well, I'm going to prove a theorem, and it's called the intermediate value theorem. And it's the theorem that tells us that a continuous function maps intervals to intervals. Well, let's first look and see exactly what this means. Suppose I'm given a continuous function f and an interval in the domain. I want to show that the image set is also an interval. Now what does that mean? It means that if I take 2 points in the image, then any point between them is also in the image. Let's put that in symbols. If the 2 points in the image are f of A and f of B, then the theorem says that any intermediate point D is the image of some point C in between A and B. So here are the points we start off with. We've got 2 points A and B in the domain, their images f of A and f of B in the codomain, and some point D between them. And what we actually want is to find some point C that maps by f to D. Well, that's intuitively obvious. You see, the function's continuous. There's no gaps. And so, opposite D, the some point of the graph, and hence it comes from some point C down here. But that's just intuition. What we're going to do is we're going to give a formal proof. And like many of the proofs in this unit, it's going to break up into 3 parts. First of all, we're going to construct a bisection nest. Then we're going to use the completeness axiom. And finally, we're going to use the definition of continuity. So let's start off with the bisection nest. What we're going to do down here is to find a bisection nest that somehow traps the point C that's going to map to D. So let's start off by looking at this interval, A to B. You see, the point A maps to here, the point B maps to here, and so the images straddle the point D. Well, we want a point C that maps to D, so it seems very obvious to look for one in here. So, as the first interval of our bisection nest, we'll choose this interval from A to B. Well, that was very easy. Now we've actually got to make some real decisions. How are we going to get the second interval of our bisection nest? We're going to have to choose between the left-hand half and the right-hand half. And to do that, we're going to use the following decision procedure. Well, I'll go into that in some detail. First of all, what we do is we look at the midpoint of this interval. And then we see what its image under f is. It's a point up here. And then we ask which of these half intervals is such that its endpoints give images still straddling D. Suppose, for instance, D was up here. Then D would be straddled by this image and this image. So we'd want to use this half interval. Well, that's exactly what this decision procedure says. It says that if D is greater than or equal to f of the midpoint, we answer yes, and we choose the right-hand half. But in fact, in this case, D's here. It lies between this image and this image. So we want to choose this half interval. And that again agrees with our decision procedure, because here D isn't greater than or equal to f of the midpoint. We have to answer no to this question and choose the left-hand half. So this left-hand half gives us the second interval in our bisection nest. Well, we can carry on using exactly the same decision procedure to get all the other intervals in our bisection nest. At each step, D lies between the images of the endpoints of the interval. So, here's our bisection nest. What can we do with it? Well, we can apply the completeness axiom to it. Now, the completeness axiom tells us that any bisection nest converges to a unique point. And in this case, we're going to call the point C, and it's going to be our candidate for a point that maps by f to D. Well, how can we check that f of C equals D? Well, this theorem only works for continuous functions. And so far, we haven't used that fact. So it's at this point we're going to bring in continuity. So, first of all, let's have a brief look at what continuity means in this context. If we start with a nest of intervals converging to a point C and look at their least close images, then they must converge to the image f of C of that point. Since this function is continuous, we know that any nest of intervals like this bisection nest converging to C gives rise to a nest of closed image intervals converging to the image f of C. Well, how did we construct this nest? We constructed it in such a way that each of the images of the intervals contain 2 points straddling D. So D is certainly in each of these least closed intervals. So certainly this nest also converges to D, but a nest converges to a unique point. So we must have that f of C equals D. So what have we done? We've shown that for any 2 points in the image, here, then any point between them is also in the image. Well, that tells us that the image has no gaps in it. So the image is an interval. So what we've shown is that a continuous function maps an interval to an interval. And that was just the theorem that we wanted to prove. Well, in this week's unit, you'll see some remarkable consequences of this result.
So we've seen the definition of continuity of functions from R to R, and we've seen how the definition fits with our intuitive idea of how continuous functions ought to behave. So now it's time to extend these ideas to functions from R2 to R. Here's a function from R2 to R that you've met before. It's the sum function, and it maps the point xy to the point x plus y. We're going to need to prove that this function's continuous, and we're also going to need to prove that the product function, which maps the point xy to the product x times y, is continuous. We're going to need to do those things because we need to use those facts when proving some elementary properties about continuous functions. So how are we going to prove that this function is continuous? Well, it's nice and smooth. It doesn't have any breaks in it. In analogy with the definition from R to R, what we should do is to look at a nest in the domain, R2, and see whether it maps to a nest in the codomain, R. Well, there's a problem. The domain's R2 instead of R, so we need to know what we mean by a nest in R2. Well, here's the definition. What we do is we take a nest in the x-axis and a nest in the y-axis, and we take the products of corresponding intervals to give us a sequence of rectangles like this. For example, this big rectangle is the product of the 2 big intervals, the next one is the product of the next 2 intervals, and so on. Well, this sequence of rectangles has just one point in its intersection, because it's the point whose first coordinate is the point in this nest, and whose second coordinate is the point in this nest. So that's the definition of a nest in R2, and our definition of continuity is going to be that you take a nest in R2, you take the images, you take the least closed intervals, and you see whether they form a nest.
So I've got to show that this sum function is continuous. And to do that, I've got to look at a point in the domain, a nest of rectangles converging to it, and I've got to look at their least closed images and show that those form a nest of intervals. Well, that's not all I have to do. The definition says I have to do that for every possible nest converging to the point. And in practice, that might prove tedious. In fact, I'm going to be able to get away with looking at just one nest, as long as I choose one of an appropriate type. Here's the nest we're going to use. We're going to take a nest of intervals converging to x. A typical interval is of the form x minus 1 over 2 to the n to x plus 1 over 2 to the n. Then we take the product of this nest with a similar nest of intervals converging to y. This gives us each rectangle in the nest, and the nest will be of this special type because the point xy is never on the boundary of any of the rectangles in the nest. We call this type of nest a test nest, and if the definition of continuity works for just one test nest, then the function will be continuous. So, here's our point in the domain, and here's our typical rectangle in the test nest converging to that point. What we want to do is to find the least closed image of this rectangle. Well, from the shape of this surface, we can see that this corner point gives the least value of the image. That's up and over here in the codomain. And similarly, this corner point gives the largest value. That's up and over here in the codomain. And in fact, we don't have to bother about any other points, because you remember the definition tells us to look for the least closed image interval. Well, we found this point, the smallest point in the image, and this point, the largest point in the image, so this interval is the least closed interval containing the image. Well, we can do that for every rectangle in the nest. And the sort of interval we end up with is one from x plus y minus 1 over 2 to the n minus 1 to x plus y plus 1 over 2 to the n minus 1. And we have to ask, do these intervals form a nest? Well, of course they do. They're exactly the same type of nest as we looked at earlier on. Only earlier on we looked at nests converging to x and to y, and now this nest converges to x plus y. So we've shown that this sum function is continuous at the point xy. And of course this was an arbitrary point. So the function's continuous at every point in the domain R2. Well, can we use this same technique to look at other functions that you're familiar with? For instance, the product function. So, here's our humpy surface representing the product function. And we're going to use exactly the same technique to show that this is continuous. But in fact, our proof's only going to work in this, the first quadrant. But that doesn't really matter, because it's a beautiful symmetric surface. You see, for instance, if I rotate it round like this, the third quadrant looks exactly like the first quadrant after a rotation. And if I look at this quadrant, it looks exactly the same, only now it's upside down. That is, it's the same after a rotation and a reflection. So, let's go back to the first quadrant to get on with the proof. Here's our typical point xy. Here's our typical rectangle in the test nest. And because of the shape of the surface, we can again see that this corner point gives the least image. That's up and over here in the codomain. And this point gives the largest image. That's up and over here in the codomain. So we're interested in the least closed interval containing the image, so it's just going to be this interval. Well, we can do that for every rectangle in the test nest. And when we do, we get an interval of the following form. It's from x times y minus x plus y over 2 to the n plus 1 over 2 to the 2n to x times y plus x plus y over 2 to the n plus 1 over 2 to the 2n. Well, do these intervals form a nest? They do. And to see that, we just have to look at their length. The length of a typical such interval is x plus y over 2 to the n minus 1. So at each step, the length halves. So we've got a nest. So we've shown that this product function is continuous at the point xy. But this was an arbitrary point. So in fact, we've shown that the product function is continuous at every point in the domain R2.
So continuity of functions from R2 to R is just a straightforward extension of continuity of functions from R to R. The only difference is that we have to use a nest of rectangles in the domain instead of a nest of intervals. And you may have guessed that we're going to use the same idea when we come to functions from R to R2. Here's a typical function from R to R2. This is the domain, and here's the codomain R2, and here's the image. And what we have to do is to take a nest in the domain, like this, and look at the images. So if we take a typical interval in the nest, it's going to have as image some part of the curve, like this. And a smaller interval is going to have a smaller image. And what we're going to do is we're going to have to take the least closed rectangles containing those images and then look to see whether they form a nest. The way you construct the least closed rectangle is to take the least closed interval containing the horizontal projection and the least closed interval containing the vertical projection. The product of these two intervals is the least closed rectangle. If we repeat this for each of the image sets, then we'll get a nest of rectangles exactly when the two collections of intervals form nests. So the function's continuous if and only if this sequence of rectangles here forms a nest, and that's the same as saying that these two collections of intervals form nests in the x and y axes independently. So in other words, the function's continuous if and only if the two coordinate functions are continuous on their own. Well, that's a very brief sketch of a theorem which we'll pay greater attention to in the text. But the idea is the same as for functions from R to R. You take a nest in the domain, you look at the images in the codomain, close them off, see whether they form a nest. Well, in this program we've had a brief look at continuity, and that's one of the key ideas of analysis, and you'll find that the ideas in continuity are used time and time again in the other main areas of analysis.